Welcome to the lesson on binary system and computers. The lesson will be covered by me, Mohammed Dani bin Apadi, and my friend Hu Yong Chuan. So what you learn, what the binary system is, why do computers adopt the binary system, and the ones and the twos complement. So why do computers adopt the binary numeral system? Computers all run on electricity, which means they operate based on the principle of on and off. Inside a computer, all we have are electronic circuits, which means there are only two states, on and off. Therefore, the only way that a computer can represent and handle numbers is to use the binary system, as they only operate in on and off states. With the binary system, there's only two numbers. So what the binary number system is? It's a method of counting in the base of 2 using only numbers 0 and 1. In computing, each 0 and 1 is referred to as a bit. After a digit reaches 1 in binary, an increment resets it to 0. So each digit of 0 or 1 represents an increasing power of 2, with the rightmost digit representing 2 to the power 0, next representing 2 to the power 1, then 2 to the power 2, so on and so forth. In order to determine the decimal representation of a binary number, we multiply the binary digits with the powers of 2 they represent. So in this example, we have the number 6. So this 0 over here represents the position of 2 to the power 0. As it is a 0, the value is the numerical value of it is 0. Thus the value in the base of 10, thus the value, if you convert it to the base of 10, is equal to 0 also. Next we have the number 1 in the position of 2 to the power 1. Thus if we convert it to the base of 10, 2 to the power 1 equals to 2. So we add this to the sum. Next we also have another one in the position of 2 to the power of 3. The value in binary is 1. Thus in the base of 10 is 2 to the power of 2, which is equal to 4. If you add the 4 to the previous sum of 2 in the previous calculation, you have 6. Next, so far the sum is 6. Next we have the position of 2 to the power of 4. The value in binary is 0, so thus the value in the base of 0 is also 0. So altogether we have the total sum of 6. So in conclusion, 0, 1, 1, 0 represents 6 in base 10. Over here you can actually see the working broken down. So 2 to the power 0 times 0, 2 to the power 1 times 1, cause is represented in 1 in the binary number previously. 2 to the power 3 times 1, and 2 to the power 4 times 0. Add them up, you get 6. So next we're going to talk about sign representations. Sign representations are compulsory for computers to encode negative numbers for binary numbers, as using symbols is not possible as numbers are represented as bits. As I said earlier, computers only operate in two states, on and off, so they can't really adopt the base 10 number system. There are many systems of sign representation. However, we are only going to focus on the three most common ones: the sign magnitude representation, the ones and twos complement, and the twos complement. In sign magnitude representation, we denote whether the binary number is positive or negative by its leftmost significant bit. 0 is used to denote a positive number and 1 is used to denote a negative number. Thus, for example, if we were to encode 84 in an 8-bit byte, it would be 001 01010. So if we were to break it down and change it to a negative number, negative 84, we change the leftmost bit over here to 1. So 1 becomes the negative sign, then the rest of the numbers represents 84. One main disadvantage of using a sign magnitude representation is that sign magnitude has two representations for 0, 1 0 0 0 0 0 0 and 0 0 0 0 0 0. This makes it very difficult and complex for computers to carry out arithmetic logical operations.
Okay, so now I'm gonna talk about the first complement and the second complement. How do we represent integers in the first complement? The first complement representation is like the reverse of the sign and magnitude representation. It works by inverting the bits in binary representation. To represent a negative 6 in first complement, first look at the binary representation of 6. Its sign and magnitude representation is 0, 1, 1, 0. After that, you convert the 1s to 0s and the 0s to 1s. So how you represent negative 6 in first complement is 1, 0, 0, 1. Comparing the second complement to the first complement, the second complement is most often used due to the disadvantage in the first complement. The first complement has two 0 values, a negative 0 and a positive 0, whereas the second complement only has one 0 value. So how do we represent integers in the second complement? First, represent the integer in its first complement. After that, you add a 1 to it. Representing a negative 6 in second complement. First, look at its sign and magnitude representation, which is 0, 1, 1, 0. Convert it to the first complement, it becomes 1, 0, 0, 1. After that, add 1 to its rightmost significant bit, which results in 1, 0, 1, 0. So that is the second complement's representation. So now I'm going to talk about the addition in second complement. So to add the two numbers, simply just add their representations in the second complement. So this is an example. As you can see, 0, 0, 1, 0 is the second complement of 2, and 3 represents 0, 0, 1, 1. After you add the results, will turn into 4, which is 0, 1, 0, 1. So to subtract is also about the same. Simply deduct their representations in second complement. So the second complement of 3 is 0, 0, 1, 1. You minus away 2, which is 0, 0, 1, 0, which results in giving you an answer of 1, which is represented by 0, 0, 0, 1. So now I'm gonna talk about overflow. In second complement, the bits can only represent the values ranging from a certain number. So the formula for that is over here in this slide. Also, an example is numbers that can be represented by 8 bits are 127 to negative 128. So what exactly is overflow? Is when the given answer of the result is not in the number range for the bits.